All right, thank you. So I'm super excited to be here and to see all of you here and to talk about one of my absolute favorite topics in the world, which is dynamical systems. So I love dynamical systems. It's why I am where I am today, is to study things that move and change in time. And so I prepared this tutorial and tomorrow's tutorial on dynamical systems to have a pretty healthy mix of kind of intro material that lots of you will know with some advanced material that maybe some of you don't know. Also a lot of old historical material mixed in with the new and up and coming techniques that people are using. And so I really, really want you to ask me questions and interrupt and tell me what you're interested in, because basically I've organized a bunch of little mini tutorial lectures, and I can mix and match them if you find one area more interesting or less, or if your background is deeper or shallower, and so on and so forth. So please do interact with me. And I'm going to ask you questions, and I'm going to expect you to raise your hand and tell me how much dynamical systems you know and things like that, because that's going to help me tailor the material a little bit better. Okay. So dynamical systems, I'm going to mix a little bit on the screen and then on the board, do some by hands. My definition of a dynamical system is very, very simple. It's any system that evolves or changes in time according to some rules. So pretty much anything you can think of is a dynamical system. Okay, you can definitely think of things that are not a dynamical system. Your chair is not a dynamical system until you sit in it. Then it is, for that moment that it moves, a dynamical system. But you have earthquakes for that, so it can be forced and become a dynamical system. It has a spring constant. Okay, so anything that changes in time according to some rule is a dynamical system. And I'm going to give you a lot of cool examples that motivate me in my daily work. So again, a quick show of hands. How many of you work with dynamical systems on a kind of daily or weekly basis? It's part of your bread and butter. Beautiful. How many of you have learned about dynamical systems in school, but maybe haven't used them for a long time? This is kind of undergrad material. Okay, excellent. How many of you really couldn't write down the solution to an ODE if I woke you up at 2 in the morning and forced you to? Okay, good. So I'm gonna have a little bit of something for everybody. All right. It might happen. So okay, good. So I'm just going to give you some examples of dynamical systems. I actually realized that at the beginning, all of my pictures were pictures, and in reality, I should be showing you movies, because dynamical systems are essentially movies of systems evolving in time. So I love roller coasters. I think we should all go to Magic Mountain sometime while we're here. Fluid flows are high-dimensional, nonlinear dynamical systems that describe, for example, in this case, the evolution of vorticity, or how much the fluid swirls at each point in space and time. Couldn't find a good movie, but imagine your brain is an incredibly complex, multi-scale dynamical system. It's constantly changing states, so if you're paying attention to what I'm saying, you're in one state of mind. If you're kind of relaxing and zoning out, that's a different state of mind. And the evolution of those thought processes and how you learn and interact with the world is an extremely interesting dynamical system. Something important to mention about the brain, and this is a theme that I'm going to bring into this entire discussion on dynamical systems, is that I think of dynamical systems most often in terms of engineering objectives like optimization and control. So you can't just study a brain in isolation. People tried to do this. You take a dead fish from the supermarket and you can study its brain, but you don't learn that much. Okay? What you want to study is how this brain uses its robot body to interact with the world. That's much more interesting. So dynamical systems generally are interfacing with some external environment that might be causing it to have stochastic forcing, slow varying parameters, and maybe the dynamical system wants to achieve some task. There's also other interesting examples of high-dimensional dynamical systems like disease modeling and spread, climate science, social networks. These are all high-dimensional, nonlinear, multi-scale dynamical systems that evolve in space and time. Okay, so that's going to be my theme. High-dimensional, nonlinear, multi-scale dynamical systems that evolve in space and time. Okay? This is one of my favorite images from Philippe Dutoit, who is a PhD student at Caltech. And he basically showed these invariant manifolds in the ocean. This is, again, should be a movie, but each frame takes a supercomputer, maybe a week at the time he computed this to compute. So the ocean is a dynamical system. The atmosphere is a dynamical system. And there are extremely important kind of societally relevant things that matter from dynamical systems. Like we want to be able to predict the future evolution of the dynamical system. We want to be able to put some uncertainty bounds on our future prediction. If I take actual measurements of my system and I have a model, I might want to be able to reconcile those two. That's like the Kalman filter. And again, eventually I might want to change the optimization of a system. I might want to change what I'm doing to the system to optimize or control its behavior. Okay. This is, again, one of my favorite videos. I do a lot with inverted pendula because they're really fun and they're really easy to analyze. So this is a SpaceX rocket, and I claim that this is basically an inverted pendulum, right? You're putting force at the bottom of a long stick. And in this case, they're going to try to land the inverted pendulum. And this is a pretty interesting and challenging control problem. So the model has to be pretty accurate. And my model prediction has to be fast enough that I can use this enclosed loop for real-time feedback control, in this case, to slowly and gently land a rocket. Okay, a human walker is a very interesting control system. So I am approximately some double or triple pendulum with spring, mass, torque dampers in my body. And I'm neutrally stable. So if you shot Novocaine into my legs, I'd fall over. Okay, but that neutral stability allows me to move very, very efficiently. So that's also an important aspect. There are instabilities in the system, right? If you pushed me and I wasn't using the muscles in my foot and leg, I'd just fall over. But that instability is what allows me to walk very, very efficiently, because all I have to do is kick myself just a tiny bit off in the unstable direction, and I get a lot of transport essentially for free. Okay, so that's another concept that we're going to use a lot, is instability in dynamical systems. I like to think of the kind of astrophysics applications and motivations of dynamical systems. So a lot of what I'm going to tell you today and tomorrow is going to be about parallels between how we learned basic physics, F equals ma, Newton's law, general relativity physics, which are dynamical systems, and parallels with how the state of the art in machine learning and artificial intelligence are evolving today. Okay? So there are these deep parallels between the giants of classical astrophysics, Kepler, Newton, Ptolemy, and others, and kind of these different perspectives on machine learning that we're using today. So I'm going to bring a little bit of that in. And again, this picture looks static. It doesn't look like a dynamical system. It's not a movie. But for example, and also if we measure these objects, they don't move that fast, right? Like as far as we're concerned, they're essentially stationary. We're rotating, of course. But if you measure their redshift, then you can start seeing that everything is actually moving incredibly fast and accelerating according to these basic laws of motion. Okay, so this is data that has been the underpinning of all of our knowledge of dynamical systems for thousands of years, was essentially started here. Okay, so I love dynamical systems. They're super interesting, all kinds of fun things you can do with them. And I'm going to start walking you through an overview of what I'm going to talk about for the next two tutorials today and tomorrow. And then we're going to jump into a couple of examples, just kind of baby dynamical systems where we can look at a few interesting things that you might do with them. And then I'm going to start building up the modern data-driven dynamical systems perspective that's probably most relevant for all of us. How do you actually discover dynamical systems from data? How do you find the right coordinates where they become simple? Things like that. Okay, any questions before I jump in? Everyone's ready? Okay, good. How many of you love dynamical systems? Okay, good. I hope all of you love dynamical systems by the end of this workshop. Okay, so when I say a system that changes or evolves in time, of course I need to describe the state of the system. So I'm going to start with a differential equation in terms of some variable x. I'm going to use underbar to denote that this is a vector of states. And I have ddt, the time derivative of that state x, is equal to some function of x, of time, of some control input u, and probably of some parameters b. And so I want to just go a little bit slowly through all of this so that all of us are on the same page. So x is the state of my system. And generally, when I say state, I mean the minimal description, the minimal set of variables I need to describe my system. Okay, so if I have a cannonball, I need its position and its velocity in 3 components. So that's 6 variables I need to characterize. Okay? If I have a pendulum, then I need to characterize the system by its angle theta, but also by its velocity, its angular velocity theta dot. I need to know if it's going this way or this way. That's the minimal state of the system, and I would append those as terms in X. Yeah?
So are you going to be talking about continuous time?
So for now, I'm talking about a system that continuously evolves in time according to this differential equation. But there is another formulation in terms of discrete time where I maybe measure my system at a fixed interval, or my system is seasonal. Like if I want to measure the bunny population in Seattle every March, that's a discrete time dynamical system. So essentially, you could write that as xk plus 1, x at time k plus 1 equals some function of the previous state. Yeah, so this is discrete time, this is continuous time. And you can kind of often go back and forth between these. Okay, good. And when I say that the state is the minimal state used to describe the system, often what I mean here is that my future state, or the time derivative of my state, only depends on the current measurements I have at time t. Now, so that's very important, is that this x is measured instantaneously now, and I'm assuming that all of the information I have now is what I need to predict the system in the future. So that's true for the pendulum, right? If I know theta and theta dot right now, I can tell you what's going to happen in the future. But that might not be true of the stock market. Okay, so if I just give you the stock prices right now, I need to know if they were going up or going down. I need to know what Trump was tweeting. I need to know all kinds of stuff about the past to inform that. So that's not a minimal state of the system. Okay, so I'm assuming that there is no history dependence here. Okay, good. Now, in general, this function f, these are what I call the dynamics. And in some sense, I think of this as a vector field because it's a vector of values at every point in space and time. And it allows me to move along like a vector field. And generally, the dynamics encode all of the physics and constraints of the system. So if I have conservation of energy, if I have symmetry, if I know that my pendulum is forced to be on a circle, all of that comes into these dynamics F. Okay, this is where you encode your knowledge of physics and constraints. These dynamics can change in time. So maybe I should draw a little picture of a pendulum. Okay, so that's my pendulum, and it's moving according to gravity. But if there's an earthquake, these dynamics are going to change in time. Okay, everything. If the gravity of Earth changes slightly, if I do this on a spaceship or on an airplane, then these dynamics are going to change slowly in time. U is often my actuation or control input. So this is usually what I think of as I have control over U. I get to do something to the system to change its behavior. Maybe I can move the base of this pendulum. Maybe I can apply a magnetic field. Maybe I can do something like that. And then finally, beta contains all of the parameters that are relevant. So the mass, the length, the strength of gravity, things like that. Okay? And this is the basic formulation of a dynamical system that we can use to describe all of the systems I showed you. They're much more complicated, but that's the basic underpinning. Yeah, question?
Is there anything special about beta that you could just fold it into F?
You absolutely could fold all of these coefficients beta into the coefficients of F. But what I'm really interested often is how the qualitative dynamics of F change as I vary these parameters. So I want to look at the explicit dependence of F on these parameters. Yeah, so for example, I want to know, does my stability change at some point if I change the length of the pendulum arm? Things like that. So it's really important for analysis, design, and control, essentially for guarantees. I want to understand that my system's not going to break if I change these parameters.
But you're not going to say, what if gravity operates in the opposite direction, right? Because that's not an interesting thing.
You could ask that question, but that might not be the most relevant question to ask. Yep. You had a question?
So, dynamics of
Yeah. So this is a great point, and I was going to wait to talk about this, but maybe I'll talk about it now about deterministic versus probabilistic systems. So I'll give you just a couple of maybe in a couple of minutes I'll tell you about the probabilistic analog of this. Yeah.
So you don't assume anything about the kind of manifold that X is living in?
So there are some assumptions. X is the state, and it could live in a vector space. It could live in Rn. X could live on some manifold. It could be, the fluid flow on the surface of Earth. Like I would need to consider the topology of, the geometry of the manifold I'm working on if I was, for example, simulating hurricanes. Yeah, so usually I'm going to punt and just say that this can be embedded in a sufficiently high vector space, and I'm just going to work on vectors because it's easy, and that's often what we do. But sometimes you actually need to take into account the geometry of the manifold that the state lives on. For example, I'm implicitly assuming that theta, or x here, lives on a circle rather than in a continuous line. Okay, great questions. Other questions?
And the U depends on x and t? Or?
So U, right now, I'm going to say is a function of t that I get to play with. But sometimes I'm going to build a little widget that measures x and feeds it back. And that will be feedback control. Great. In the back. Yeah.
You can fold it into x also.
You can always, if U is a function of x, then this all becomes just a function of x. Yeah, that's right. So again, I'm separating out the things I have control over versus the things I don't have control over versus the things that I might want to be robust to changes in and time. Yeah, all really, really good points. Okay, I'm going to get to the probabilistic description in a minute. Okay, and I'm going to talk right now about some of the challenges of these systems. So the modern challenges that we have, that I'm going to repeat these over and over for all of this lecture and the one tomorrow. So you're going to hear this a bunch from me. So I don't think of these as problems. I think of them as challenges. The first, most fundamental challenge is that usually we don't know F for the systems I actually care about. Okay? So one, we don't know F. Now you might be saying to yourself, we know lots of Fs. We know F equals ma. We know quantum mechanics. We know general relativity. We know all of these basic equations, Navier-Stokes equations that describe how physical systems evolve. That's true. We don't have an equation for the brain. We don't have an equation for how disease spreads. We can't agree on equations for climate. Okay, and even the equations we do have access to, the Schrodinger's equation and the Navier-Stokes equations that describe these complex systems we want to interact with, those equations are not at a resolution that's useful for us as practitioners. So solving the Navier-Stokes equation as a PDE makes great movies, but it's very, very hard to use that for real-time optimization and control. So I want a reduced description that's useful for the things I care about. So I would argue even in the cases where we do have the governing physics, we might not have a description in terms of an effective state that's useful for us in our daily lives. And so I'm thinking of F as my model of reality. And this model doesn't have to be perfect. There's always a balance between accuracy and how complete the description is, and how complex or slow or cumbersome or detailed the model is. And so there are different levels of resolution. Even if I have the Navier-Stokes equation, very accurate, very cumbersome, I might want to find a reduced order model that I can use for my quad rotor control loop. Okay, question? Good, okay. So a lot of what we're going to talk about in this entire 3-month workshop is based on the fact that we don't know F, and we're going to discover it from data or effective reduced order models. Okay, 2 is that F is often nonlinear. Okay, so nonlinear F. And depending on which day of the week it is, I might alternate which of these is a bigger problem for me. Okay, so nonlinearity is what keeps us all in business. Fundamentally, you have job security. We all have job security for our entire lives, presumably, because F is nonlinear in most cases that are interesting. Okay? So when I say nonlinear versus linear differential equation, how many of you have a gut feeling of what I mean? How many of you would like me to just very quickly remind you why linear and nonlinear is important? Okay? So a linear differential equation is something, so if it was linear, meaning x dot is equal to some matrix A times x, or if x was a scalar, just a single value, then x dot equals lambda x, then I know everything about the solution of these differential equations if I know A or lambda. So x at any time t in the future, I hope, can people see what I'm writing? Yeah? Is simply e to the lambda t times my initial condition x measured at time 0. So if I have an initial measurement of my system, I can tell you what that state will be at all future times just by multiplying it by e to the lambda t for a scalar system, or by the matrix e to the matrix at times my vector of initial conditions. And there's some linear algebra for how you actually compute this thing, but this is completely computable, and I can tell you the solution at any time in the future. I can develop control laws with one line of Python code. Everything in life becomes easier. And the reason is because solutions superpose. If I have two solutions of my differential equation and it's linear, I can add them up, and that's also a solution to my differential equation. All of that goes out the window if my system has even a tiny amount of nonlinearity. An epsilon nonlinearity destroys all of the theory we have for generic theory of differential equations. It's unsolvable in general. Okay? Kind of a mess, to be honest. Those are the two big ones. And then I'll talk about a few more. Doesn't end there, and please do, again, interrupt. High dimensionality is a huge problem. So high dimensionality, that's just to say that x is in Rn, but n is a really big number, like a million or a billion or a trillion. So if I want to model the climate or model the weather or model the spread of disease, I need millions or billions of states that I'm measuring to know how the system's going to evolve from one time step to the next. It's very expensive, very cumbersome, and you can't use it that easily for real-time computations. So you've seen this consistently in these molecular dynamic simulations. N is ridiculously large. But we know from, for example, the theory of gases, that Avogadro's number is not the actual number of degrees of freedom I care about, right? I care about things like temperature and pressure. There are a few often leading order quantities that you can extract from that high dimensional data, and it's actually the dynamics in those coordinates that matter. And so these are all really related. Even if I knew the equations for gas dynamics of an individual gas particle, I might need to learn pressure and temperature so that I could learn the effective thermodynamic equations on those variables. Okay? So high dimensionality is a huge challenge. That goes hand in hand with multi-scale. So the gas dynamics is actually a great example of something that's super high dimensional but not that multi-scale. I can kind of homogenize over the small scales, and I get a few equations. But there are lots of systems that are inherently multi-scale. We believe the brain is multi-scale. We believe that turbulence is multi-scale, meaning that if you look at a picture of the system and you zoom in, there are structures that matter at every size scale and also at every time scale. So think of a human. Your cells certainly matter, but you don't think about your cells on a daily basis. Your organs matter, right? You want to keep those healthy. Your cells and your organs rely on your DNA, which rely on your basic fundamental chemistry, so it's multi-scale in space. It's also multi-scale in time. Right now, again, you're paying attention to the few words I just said. You're trying to connect those to something I said 5 minutes ago. But you also have days and weeks and months. You have a lifetime of timescales that are presumably relevant for you. Okay, so multi-scale that's what I'm talking about. You can't just extract one set of equations at one scale. And this is really probably the major complexity that modern methods in optimization, data science, and machine learning are opening up most rapidly, I would say. We're really starting to be able, and with just large-scale computations. Okay, we have chaos. Chaos is super interesting. I'm going to give you a whole 10-minute thing on chaos. How many of you, again, have a gut feeling of what chaos is? How many don't? All right, good. Other things, there's noise. So I really should probably have said this is plus some kind of stochastic forcing. Some exogenous forcing that I can't measure and I don't know about, and I might not even know what its statistics are. So noise and forcing. And then the last one is the fact that what I told you here, does anyone see any big problems with this? Maybe I'll let you decide what's the big glaring problem with what I wrote down. All of this is hard, but I'm making a big assumption here. Yeah?
It's somehow steady state, or you're
So steady state and transience. So transience is also very important. I want to be able to describe oftentimes steady state behavior and transient behavior, but I'm thinking something maybe even more fundamental. Yeah.
The model does exist.
That what?
The model does exist.
So the model does exist. Yeah.
The derivative exists.
Okay, the derivative exists. Again, we could go to discrete time. These are good. Yeah, in the back.
But you know the state.
Okay, so Marina nailed it. So I'm assuming that I have X, the full state of the system that I actually am going to describe everything in terms of, which is great for theorists and computationalists, but I don't often know what the right thing to measure is in an experiment. So assuming that I'm actually measuring the variables that matter to describe my system and the dynamics is a huge fundamental assumption that we usually make and don't even think about it. So I'm going to lump that all into latent variables. And I mean so many things by this, and I'm overloading this term. Maybe there are hidden variables that I'm not measuring that matter, and I have to estimate them, and I don't even know they exist. Maybe I measure far too many variables, like in the gas dynamics, and I want to distill that down to 2 or 3 or 4 variables that actually matter. Maybe I don't know what I should be measuring and writing my state in terms of. This is, in some sense, coordinates. And most of the history of mathematical physics is driven by 7, 1, and 2. Okay, Fourier transform, trying to find coordinates to make a system simpler. Okay, everything that Kepler and Tycho Brahe and Ptolemy did was essentially trying to find coordinates so that they could get dynamics that actually made sense, culminating in Newton's second law. Okay, and maybe I'll write that equation. This is important enough to write down. That usually I don't just have this differential equation. What I often have is some kind of an output equation, a measurement equation. So usually what I'll have is some y equals g of x. And again, it could depend on u, it could depend on t, it could depend on lots of stuff. I'm just going to say g of x, where y is my measurement of the system. Usually that's all I get to see is my measurement of the system y, and I might or I might not know what g is. Okay? For a long time, did we know that the temperature g was the average kinetic energy of the molecules? Right? We might not know what g is. We might just know that there's a measurement we get. All right. And there's uncertainty in everything. In beta, in t, my measurements of t have uncertainty. My measurements of x, my measurements of f, everything has uncertainty. That's a challenge too. Okay, good. That's a lot. These are a lot of challenges, but that's good. We are going to be in business for a long time. We've got lots and lots of work to do in modeling these complex dynamical systems that are multi-scale, where we don't know the right coordinates, where there's nonlinearity, where we need reduced descriptions for optimization and control. Okay, is everyone with me so far? Good. Any questions about this? Yeah.
Does the dimension of the state have to be finite?
No, absolutely not. So most of our continuum descriptions of systems, like if I have a conservation law, like conservation of mass, momentum, and energy of this gas, I write down as an infinite dimensional conservation law, and then I discretize, to simulate, I discretize into a finite dimensional n. So very, yeah, and in fact, a lot of what I'm going to tell you is taking a state X, lifting it to infinite dimensional state, often allows me to linearize my nonlinear dynamics. So if you know about the kernel trick in machine learning, this is just like the kernel trick, but for dynamical systems. Okay, good. Other questions? Yeah. Sorry? I'm going to call that coordinates. Yeah, so if I'm 80% right, I'm happy. So maybe, okay, I could give you a few example uses of these models, a few of the techniques I'm going to talk about, and then I'm going to give you your probabilistic model. Unless, who would like to see the probabilistic model first? Who would like to see the uses of the model and the techniques first? Sorry, you guys are outvoted. Okay, so the uses of the model. So I've already described most of these. I'm just going to kind of summarize them again. The primary uses of the model are prediction. And what I mean by prediction is of the future. I don't want to predict the past. We often test our methods by acting like we didn't know the past and then predicting it, but really predicting the future. And this could be a deterministic prediction. For example, in the pendulum, I can do deterministic predictions. But in statistical systems or systems with large uncertainty or chaos, I might want to do a statistical forecast. I might want to tell you the probability of being in a state or the distribution of my state as it evolves in time. So this could be an ensemble or a statistical prediction. Often, I'll want to use these models for design or optimization. So for example, I think we've heard a lot of cool examples of drug design, the design of osmotic membranes for desalination. In my field of fluid mechanics, we think of design optimization for things like Formula One cars and super yachts and aircraft and transportation vehicles. So we want to reduce drag, increase ground force and things like that. Okay, so actually a lot in my field of these reduced order models are used for design and optimization of Formula One and super yachts. Hundreds and hundreds of millions of dollars of simulations, probably Saturn V rockets, out the wazoo, to design and optimize Formula One cars and super yachts, which I think is kind of fun, but also, it's a luxury. So design and optimization. Things that also matter are where do you put your winglets on an airplane so that it has a few more percentage fuel efficiency. That translates to billions of dollars and tons of carbon. Okay, control. I'm going to talk a lot more about control. And when I say control, how many of you know what I mean? Usually what I mean is I measure the system, I make some decision based on that measurement of the system, and I change you to manipulate the system to some behavior in real time. It's basically real-time optimization. And in fact, the lines between optimization and control are becoming blurred with supercomputers and GPUs and onboard computation. And probably the thing that gets left out the most in engineering, and that I think is really important, is understanding. We don't just model to control. We also want to understand the world. We want to gain insight. We want to understand why these are the right coordinates and why this is the physics, and communicate and understand, because that will, in fact, help us do better design, prediction, and control if we actually understand the system. And so there's a few aspects of understanding, and I'm more or less speaking to the machine learning people in a lot of this. What I mean by that is I want my model to be interpretable and generalizable. Those are two of the most important things to me. So I want my model to be interpretable, and I want it to be generalizable. And I might be willing to sacrifice some percentage points of accuracy for interpretability and generalizability, because I'm going to gain later when I put this in my engineering loop. So it's so vague, and I can't tell you. That my definition of interpretability is barely interpretable. I guess what I mean by interpretability is you can analyze, make reason of, communicate, distill down, I think of F equals ma as a fairly interpretable model. Kepler's ellipses were also interpretable. Newton's second law is the ultimate generalizable model. You can learn about it from a falling apple. You can use it to design a rocket to put people on the moon. Okay, so F equals ma is kind of my model, at least of generalizable. Interpretable is a little bit more subtle, right? Usually what I mean by interpretable is sparse or low rank. I want there to be a few things I have to look at and communicate, because I'm a human, and for me, more than 3D is Heidi, okay? And then some of the techniques I'm going to talk about, and these are really techniques for what I'm going to call modern dynamical systems. So I'm going to talk a little bit more about classical dynamical systems, but modern dynamical system is really trying to solve those bullets based on data. I want to point out all of the uses of my model, except for maybe understanding, are optimization problems. Obtaining the model from data is an optimization problem. I want to find the best parameters beta or the best model f that describes my data, maybe with a penalty on complexity of f. That's an optimization problem. This is all optimization with data. And when I oversimplify the world, all I think of machine learning is optimization with data. It's a set of improved techniques for optimization and regression based on data. All of these are optimization and regression based on data. So they go perfectly with emerging tools in machine learning. Okay? So the techniques I'm going to talk about our go-to for the last, and this is not new at all, since the 60s, has been regression techniques. So the Kalman filter is essentially a linear regression that reconciles measurements of data, imperfect measurements, with an imperfect model. So regression, and I'm going to break this up into linear and nonlinear. And then there's other variants. You can add penalties, regularized regression, sparsity, regularized regression. There is an increasing movement to use neural networks and deep learning for these tasks, so I'll certainly talk a bit about that. And there's pros and cons of each of these. Neural networks, as you know, have greater expressive power, but often less interpretability and generalizability. Regression models are very, very communicatable, interpretable, and often generalizable if you regularize them, but they don't have the same expressive power. Okay? So generalizability really is about regularizing your problem. And you can regularize both of these techniques. And then a third area that I don't do as much with, but I think is super interesting, and it started off this whole data-driven discovery in the modern era, is the use of genetic programming by Hodlibson and others. Don't ask me to spell genetic programming. So essentially learning dynamical systems and conservation laws with genetic programming. Okay. Now so I said that all of these things are optimization problems. Machine learning is a growing body of optimization techniques and regression techniques based on data with fancy and improving regularization. But that's not the entire story. Dynamical systems have extra knowledge that is very, very important when you're building these models using machine learning. So for example, I know about conservation laws. I know that mass is conserved and energy is conserved in certain systems. I know about constraints and symmetries. So for example, if you trained a neural network to predict the motion of a pendulum and you gave it the x and the y position, I bet you'll get a model that is pretty accurate and gives you pretty good sinusoidal motion. But I think you're going to be hard-pressed to guarantee it's stable and stays on the constraint of the pendulum arm staying on a circle, fixed length. That's the kind of thing we know from our basic physics, lots and lots of constraints that are hard to get out of a basic machine learning architecture without baking it in ahead of time. Okay, conservation, constraints, symmetries, stability is a huge one, and so on and so forth. Okay. Okay, good. I should stop and ask for questions for a minute.
Are these all the modern techniques you're talking about?
Yeah, I mean, these are essentially some of the things I'm going to talk about. There's lots more, but I'm going to break it up into these basic categories, and there is more. Regression techniques, neural network techniques, and let's just say other machine learning techniques for modeling F, for learning coordinate systems where the system becomes simple, for handling high dimensionality, for things like that. Yeah.
If one hasn't had enough insights to model control as another differential equation, is there anything wrong with that?
No, I mean, that's the modern industrial landscape has been defined by expert humans writing down equations of motion from expert knowledge, first principles, and then designing a control law, and then implementing that in hardware. So it works. We have aircraft, we have automobiles, like that is how the modern world is built. But there are roadblocks that we hit when we try to apply those methods from a complex system like an aircraft or a car or a construction equipment to an extremely complex system like a human brain or a disease system or the climate. So absolutely, that works. If you can do it by first principles, by hand, write down the control law, like that is what we've been doing for the last forever. Yep.
Biological models where the model controlled by, as homeostasis, for instance.
Yep.
The differential equation.
Yeah, so I think of that as another form of regulatory feedback, where the control has some state that is accumulating information, some dynamical system, and then those two systems regulate each other. Yep. So the closed loop system might have different dynamics than without control. You can change the stability with control of these systems. So if I have, let's say a pendulum, you can picture I'm holding a broomstick, and if I don't move my hand, it's unstable. But if I look at the broomstick and I move my hand when I see it wobbling, I can, if I'm lucky, stabilize it for a little while. Okay. Yeah.
What is the role of like the introduction and differential equation stuff that some of us might have done in undergrad in this paradigm? Useful or?
Yeah, so the theory of differential equations, I'm going to, again, oversimplify. We understand everything about linear systems. So if I have a linear system, that A matrix, I take its eigenvalues and its eigenvectors, and it tells me what directions in state space are important, what x directions are important, and what their dynamics are. That's a very useful analogy in more complex dynamical systems. So there's fixed points. A fixed point means, yeah, I'm going to give you some basic dynamical systems overview. And maybe I'll do that sooner than later. So I'm just going to talk about a few basic things. This is going to be super fast, just a refresher of words you should know. And if you don't, please ask me, okay? And there's no real order to this, to be honest with you. So I told you that if I have x dot equals ax, this is a matrix, this is my state, then x of t equals e to the a t x naught. So this is a linear system, and there's one fixed point at the origin. So let's say I have x dot equals f of x. A fixed point is defined as some point x bar, so that f at x bar equals 0. And what that means is that ddt of x at x bar is 0. I have no motion. My system is fixed. So if I take my pendulum in the down position, that is a fixed point of the system. Technically, my pendulum in the up position is also a fixed point. It's just unstable. If you perfectly balanced it in a vacuum, it might stay there for a little while. But if you breathed on it, it would go unstable and start swinging. Okay, so fixed points are very, very, very important in dynamical systems. Often we want to model the behavior at the fixed point to see if the system will go unstable. We linearize these nonlinear dynamics around this fixed point and see if my eigenvalues are stable or unstable. Okay, so what I would do is I would look at x. I would say it's, I'd look in some little delta x neighborhood, let's say I have a fixed point, x bar, what I would do is I'd look at some little epsilon neighborhood of that, and I would plug this into my differential equation, and I would try to derive a differential equation for delta x dot, and it turns out it'll equal the Jacobian of f evaluated at x bar dotted with delta x plus higher order terms. You just get this from the Taylor series. And this is like an A matrix. So if I have a fixed point of a very high dimensional, super complicated nonlinear system, if I zoom into that fixed point, I can linearize the dynamics. For small delta x neighborhood, the dynamics look linear. You get that from the Taylor series. I skipped one step, where I plugged this in and I Taylor series expanded, and this is the leading order term in the Taylor series. And then what I do is I look at that linear dynamical system near that fixed point to see if it has any unstable eigenvalues and eigenvectors. And if it's unstable, then that means that weird stuff can happen and I can get carried away from this neighborhood and my system will go into other behaviors that might not be beneficial. If they're all stable, then that means that this fixed point at least is going to locally, trajectories are going to go towards this fixed point. So a concrete example I think about in fluid flows is the boundary layer over your wing. So this is your wing surface. This is the boundary layer, which basically says fast flow is up here, and the flow has to accelerate up to that speed from the surface to the free stream. So this is called the boundary layer. And a laminar boundary layer is what you want. This is a low drag laminar boundary layer. But if you have any turbulence or roughness or anything at all in a modern aircraft, what's going to happen is your boundary layer is going to become really turbulent and messy and unsteady. And you're going to have high drag, and it's going to bump the people around on the plane, and it's going to cause fatigue, all kinds of bad stuff. So what you might want to do is analyze the stability around, this is a fixed point. It's an unstable fixed point. I might want to understand why it's unstable, how it's unstable, and then control to stabilize it so that I avoid this on my wing. Okay? Yeah, so a lot of what we think about, how many of you know about phase portraits? How many don't? Okay, so phase portraits are kind of how I think about going from linear to nonlinear systems. So I'm just going to draw a really, really simple one. So let's say I have a differential equation x double dot equals x minus x cubed. So this is force equals mass times acceleration. This is my acceleration, and this is a force from a potential. This is a gradient of some potential phi that looks like this. So the way I want you to think about this, there's literally a wire, and there's a bead on that wire in a gravitational potential. And if I let that bead go, you can picture it moving around the surface. Yeah? It's like a roller coaster. So I can write down x dot equals some velocity, and v dot equals x minus x cubed. And then what I do with this system is I think, what are all of the fixed points? So step one is I list the fixed points. And the fixed points, so for x dot and v dot to be 0, I need v to be 0. And I need x minus x cubed to be 0, x times 1 minus x squared to equal 0. So I have 3 fixed points. X can be 0, x can be 1, x can be minus 1. So I have 1, 0, minus 1, 0, and 0, 0. This is x and this is v. Then what I would do is I would linearize these equations. I'd compute this, this partial derivative of f with respect to x at these fixed points, and I would get an A matrix, and I would look at its eigenvalues and eigenvectors to see if it's stable. And so then what you can do in x and v coordinates, I have a fixed point here at 0, 0. I have a fixed point here at 1, 0. And I have a fixed point here at negative 1, 0. And this is extremely consistent with your intuition that if I started the bead right here with 0 velocity, it would stay there. That's what 0, 0 means. If I started the bead right here with 0 velocity, it would stay there, and if I started it here. But then when I compute the linearized equations about these 3 fixed points, what I find is that this fixed point is stable. So if I add a little bit of energy to the system, it basically stays just oscillating. Same with this one. But if I look at this fixed point, it's unstable. It'll have a positive real part of one of its eigenvalues. And what that means is that if I push the system a little bit off equilibrium, it's going to move really far, really fast away from that equilibrium. And so those directions, if I computed the eigenvectors, would look like this. And then there's a conceptual leap where I can complete these circles, because I know what's happening in all of these fixed points, and I have some intuition for the system. So this is a phase portrait. You've probably seen these before. Okay? If I add friction, these turn into little sinks, and everything spirals into them. And so that's really, I mean, I'm going to, again, oversimplify a little bit, but that's kind of the state of the art. Linear systems are easy. I know everything about this system. So if I have a nonlinear system, what I do is I try to find all of the fixed points where I can linearize, and then I go and do the thing I understand in these regions, and I try to connect the dots. That's really what we do in dynamical systems. Okay? Okay, good. Any other questions? So linearization, stability, and I'm glossing over, I'm assuming most of you know that stability is determined by the eigenvalues and eigenvectors of A. So if you need to brush up on that, that'll be helpful. How many of you have heard about bifurcations and normal forms? Okay, how many of you feel pretty comfortable with bifurcations? Okay, many fewer. I'm not going to belabor this, but it is really important, and I think it's something that is going to be increasingly important in the context of machine learning, is thinking about, remember, there are parameters that might change in the system. So I don't always just care about a system with fixed parameters. Often what I want to know is how will the system change if I change the parameters of the system? Does it go from stable to unstable? That's important for me to know if I'm designing an airplane. If my airplane is stable at 1 velocity in the air, and it becomes unstable if I increase that velocity by 10 miles per hour, that's a pretty bad design. Okay? And so bifurcations, I'm just going to give a really simple example here. So I'm going to take x dot equals beta x minus x cubed. Okay, so I get to vary beta from negative infinity to positive infinity. And I want to know how this system changes as I vary beta. Okay, how many of you have seen this example? So again, I can look at the fixed points of the system. I say the fixed points are when x times beta minus x squared equals 0. So I always have a fixed point at x equals 0. And then for positive beta, so beta greater than 0, I have a fixed point at x equals plus or minus root beta. Okay? And again, I can compute the stability of each of these fixed points by basically computing the derivative of this with respect to x and plugging in these numbers. Okay, so if I looked at x equals 0, then my derivative of my vector field with respect to x is just, my derivative is always beta minus 3x squared. And if I evaluate it at x equals 0, I plug x equals 0 in here, then this equals beta, which might be positive, might be negative. If x equals plus or minus root beta, then this will equal beta minus 3 beta, which is minus 2 beta. And I said this was only for beta positive. And so a negative 2 beta is definitely a negative number, which means this is always a stable fixed point. And so what you can do is you can plot these trajectories on the beta line. And let's say this is beta equals 0. And the y-axis, I'm going to say, is the fixed points of x. So if beta is negative, there is one fixed point. There's only one value that satisfies this when beta is negative, and it's x equals 0. And for beta negative, the fixed point at x equals 0 is stable because its eigenvalue is stable. I get basically x dot equals beta x locally near x equals 0. And so I have a stable fixed point. As I increase beta through 0, I pick up 2 additional fixed points, plus and minus beta. So I have 2 new fixed points that branch out x equals plus beta, root beta and x equals minus root beta. And I claim because I plugged in that value and I get a negative number, that eigenvalue is stable. And so these branches are stable fixed points. And the fixed point at x equals 0 becomes unstable when beta goes positive, because now my eigenvalue is positive and this blows up exponentially. And so now this becomes an unstable. That's just what a dashed line means in dynamical systems. And so this is like the simplest example you can cook up, where you have a very simple differential equation, but now there's some parameter you get to play around with. And as you go from negative values of that parameter to positive values, really weird, qualitatively different things happen. So a bifurcation is one of these points where the dynamics qualitatively change. You get new fixed points, your stability changes, things like that. And these are what you're looking for in lots and lots of engineering systems. Like a seizure might be described by a bifurcation in the dynamics. Your aircraft might go through a bifurcation in the dynamics where the instability, like the flutter on the wing, starts to amplify and the wing rips off. This happened a lot in the 30s. Actually happened to the A380 before they redesigned it. Bifurcations happen everywhere, so it's really important to understand what parameters actually change with your system and what the sensitivity of your dynamics are to those parameters. Okay? That was really fast. But that's all I'm going to tell you about the background on dynamical systems. Okay, any questions? So the words you need to know: linear systems, eigenvalues and eigenvectors. Stability of fixed points, which are determined by those eigenvalues. Phase portraits for nonlinear systems, and bifurcations and normal forms. Okay, good. So now I think I'm going to tell you a little bit more about kind of what I think of as modern dynamical systems, and this is going to set up what we're going to talk about in the next part of this. Okay? Yeah.
You talked about linearizing a problem around a fixed point.
Yeah.
And so does that mean that you do this also? So you do this in the case where your problem is non-linear, but you still sort of like you linearize it around a fixed point?
Yeah. So there's a lot of theory I'm completely glossing over that's very, very interesting. And so there's something called the Hartman-Grobman theorem, which basically says, depending on certain properties of my dynamical system, if I zoom in close enough to a fixed point of a nonlinear system, I can describe it by its linearization. And so it looks linear if I zoom in enough.
Does that provide some bounds or some metric as to how far you can go around the fixed point? Or?
Yeah, so there's a whole theory called normal form transformations, which allow you to change your coordinates to make that window of validity bigger and bigger and bigger. And that's actually what they've been doing in space mission design for a long time. There are a bunch of fixed points in the solar system, and what they do are these normal form transformations to make them as linear as possible for as large of a radius as possible. Yep. Any other questions? Okay, so some things I'm going to talk about are kind of this progression of complexity from an increasing nonlinearity, from linear systems where we know everything. And notice I put the pendulum here. This is linear for very small amplitudes. It becomes nonlinear as you make the amplitude bigger. Kind of weakly nonlinear systems where there's a few fixed points, but it's relatively periodic or quasi-periodic, to full-blown chaotic systems like the double pendulum, the Lorentz system, things like that, which I'll talk about a little later. In practice, what we often do in dynamical systems is if we have the equations of motion F, what we'll do is we will integrate trajectories through that dynamical system. So using modern numerical integrators like Runge-Kutta, fourth order Runge-Kutta or Euler, what I can do is I can take these dynamics and I can cook up some scheme to step x forward one delta t at a time, one small time step at a time. And so in this case here, what I've done is I've taken a grid of initial conditions in white, and I've integrated them along some fluid velocity field. This is flow past a wing. This is like a mosquito wing or a moth wing. And you can see a lot about the dynamics based on where those particles go. So for example, you can color code regions where a lot of stretching occurs, or there's a lot of sensitivity and you need to measure or control in those locations. Okay, so a couple things I want to point out, and I'm going to end soon. In modern dynamical systems, the first thing I want you to know is that if you want to know more about any of the stuff I've been talking about and any of the stuff I will talk about, we just wrote a book, Data-Driven Science and Engineering, and this is not just a shameless plug for the book. I have put up a complete copy of the PDF on my website, so you can get it for free. You don't have to buy it. If you like it, you can. But you can get the entire PDF here, and it has everything I'm going to talk about, and it goes into a lot more depth about how you linearize around fixed points, why eigenvalues are important, all of this stuff. So if you feel like I rushed over that and you didn't catch it, chapter 7 is going to walk you through all of it. Okay? And at databookuw.com, we actually have videos for every section of every chapter of the book. So all of these are on YouTube if you want to like walk through really, really carefully all of this information. So slightly shameless plug, but a lot of free material out there if you think I went too fast. Okay, so the things I think about that I'm going to talk about for the rest of my time today and then for the entire tutorial tomorrow are really these basic themes. And so I'm going to take from those challenges 1 through 7 on the board. I'm going to pick my favorite ones, and that's what we're going to talk about. Okay. The first one is that often equations are unknown or partially known, or the form of the equations is not useful for me. And so we're going to talk a lot about model discovery using these techniques of linear and nonlinear regression, genetic programming, neural networks, and so on and so forth. The other aspect that I'm going to focus a lot on is the aspect of nonlinearity. So again, nonlinearity immediately hampers our ability to cook up generic, simple solutions and predict for arbitrary times in the future. And so what I'm going to talk about are ways that people are using data-driven methods to discover effective coordinate systems that simplify your system. Now, simplify means very different things to different people. Okay? For me, as a control theorist, if I can linearize my dynamics, that's like the ultimate simplification, because I know everything about linear systems. Sometimes making my system sparse would be a simplification, because there's less terms I have to analyze and think about. And again, the history of mathematical physics is defined by moments where people had epiphanies where they came up with a coordinate transformation that explained their system and made their system simple. Okay, so if you think about the Fourier transform. The Fourier transform is my favorite example of this. Fourier didn't do this for no reason. He cooked up the Fourier transform to diagonalize the heat equation. It is the coordinate transformation that makes the heat equation simple. And in his case, simple means linear, diagonal, decoupled, and sparse. Okay, and it's with us today. And so increasingly, we are able to discover these coordinate transformations and represent them in these more powerful representative architectures like neural networks. And then the last one is the challenge of high dimensionality. So high dimensionality often obscures our understanding of the dynamics. Think about the gas dynamics example. It took a long time to go from individual atoms to a thermodynamic description. But we know that patterns exist in most systems we care about, and that facilitates reduction. Okay, so I have a little bit more time. I guess I have 10 minutes. Are there any questions before I go into more technical stuff? Yeah.
So for the high dimension, are you interested in deep field, infinite dimensions, deep field?
Yeah, so this should be simplify, and then my definition of what simplify means is it changes every day of the week. Sometimes simple means mean field, sometimes simple means higher dimensional but linear, sometimes simple means probabilistic. It really, whatever I can get an effective model that allows me to solve some of my objectives of design, optimization, and control, that's what I want. Sorry, I never got to probabilistic description of dynamics, and I might not have a chance to at this moment. So I'm going to do a choose your own adventure. There are a few things I can talk about. I could talk about chaos and give you some cool movies. Or I could talk about control and give you some cool movies. How many of you would like control? Good. How many of you would like chaos? All right, control has it. And I'll start off next lecture with chaos. Okay, good. So this is an experiment built in my lab by Cardi Kamen. This is a double pendulum on a cart that you can actuate, and you can essentially swing this thing up and stabilize it. Again, there is a fixed point with both of them up, but it's unstable. But by measuring the system, there's little encoders that measure the angles here and here. I can measure that, and with a model of the system, I can feed that back and change the dynamics and stabilize it. Pretty cool. So that's one of the things you would want to do with a model. So how many of you have some expertise on control and feel pretty comfortable with it? How many would like to learn more about it? Beautiful. Okay. So there's a lot of dichotomies in control that you can talk about, and I'm going to just give you the most kind of naive division of these. There is active versus passive. So passive means you're not putting any energy into the system. It's a stop sign. A stop sign is a passive control. Active would be a stop light. Okay, so you're actively putting energy into the system and changing the control input. So a stop sign is passive, a stop light is active. And then in terms of active control, there's open loop and closed loop. Open loop just means that you have a pre-planned control strategy that you hope works. So my stop light just turns red for a couple, 30 seconds, then it turns green for 30 seconds, then it turns red, then it turns green. That's open loop. That's not how it works in Los Angeles. There's measurements in the road to see what the traffic flow is to make it faster, but a normal traffic system with a simple, dumb stoplight is just open loop. The controller does some pre-planned thing to give the desired output behavior that you want. And you'll get a better job if you have a model of your system. Okay, so another example I think of is like a toaster oven. If you want toast at a certain level of doneness, of toastedness, your toaster oven basically just sets a timer and cooks it for that long, and usually it comes out about right. Okay, there's a model for how fast things toast. But then if you put another piece of toast in right after, what happens? Gets a little burnt because the toaster's hot and your model's wrong, okay? Unless you have a super fancy toaster like my grad students just bought, in which case it measures the temperature and changes the time for that system. So there's a lot of challenges and problems with open loop. It relies on a good model, but it fundamentally can't stabilize unstable dynamics. So in my pendulum on a cart example, there's no way of stabilizing that system without actually taking measurements of the system. There's no perfect pre-planned trajectory that can stabilize an inverted pendulum so that if you blow on it, it doesn't fall, because it can't know that you're going to blow on it. Okay? And it tends to overreact to noise and disturbances, and it's not robust. So the solution, what we all do, is we measure the output of the system Y, and we feed that back into the controller. So now the controller is actually measuring the response, seeing if the system actually did what you told it to do, and then it changes its control input to modify the system based on this kind of discrepancy between what it thinks the model should be doing and the measurement of the actual system. Okay, so this is very, very standard feedback control 101, is that you get a lot of benefit just by measuring your system, kind of obvious. But again, you're now reconciling a discrepancy between your model of the system and the output of what the system actually does. Okay, so with feedback control, you can stabilize unstable dynamics, you can compensate for uncertainties, you can handle sensor noise and disturbances. So if you're in a windy room, you can stabilize the pendulum on a cart, and you can push on the pendulum a little, and the system will react. Okay, these are all the things that control is good for. Okay, now the standard industry control, there's two standard algorithms that almost every industry in the world uses. The first one is PID, proportional integral derivative. That's been around forever. And the second one is model predictive control. So most like construction equipment and chemical plants and advanced process and manufacturing uses model predictive control. Advanced robotics uses model predictive control because it allows you to use a model that you have for your system even when the model is nonlinear and there's constraints and there's things you have to, like if I can only control so much or my robot arm can't hit a wall, I can build those constraints into this model predictive control optimization. And so the basic idea here, as you might guess, it's based on a model. So what model predictive control does is you have some goal that you want to achieve. You want to drive your system from here to here. And so what you do is you set up this really heavy optimization where I try a bunch of different control laws over a finite time horizon. I see which control law in my model gets me closest to where I want to be, and I take one step in that direction. That's this first step here. Then I reinitialize everything. I rerun a bunch of optimizations with these new control laws. I take the one that gets me closest to where I want to be, and I take another step in that direction, and another step, and another step. And I can build in constraints. I can do this with nonlinear systems, and it's extremely robust to relatively poor models, all kinds of stuff. And this is the backbone of like modern industrial control design is model predictive control.
Sorry, you said a space of control laws. Can you just be more precise by control law?
Yeah, what do I mean? I basically try a bunch of U of T's in open loop often. Like I cook up a bunch of U of T functions of things I could try for control, and I pick the one that does the best, and I apply that control law for a little bit of time.
So if you had a kind of bang bang control thing, it would just be all.
It would pick it would basically decide what bang bang sequence gets me closest to the objective, and then it would start doing that bang bang sequence for a little while, and then it would rerun that optimization in kind of a moving window. Yeah, so that it's really robust because even if your dynamics aren't that great, if you're moving in the right direction, model predictive control will keep moving in the right direction. You had a question.
Keys are defined all the way up.
So there's a lot of parameters you get to choose, which is your prediction horizon for your model, how long you apply that control law before you re-optimize, and the ultimate horizon for your set point. And those are all depending on how much computation you have on board, how fast the timescales are, because this is all limited by how fast you can run this optimization. Okay, so this is one of those cases where you don't want the best model possible if it's really expensive. You want the best model that gets you close to the right direction as fast as possible because you're running this real-time optimization, this massive optimization. And so what people actually do now is build essentially deep model predictive controllers where they use deep learning for the model, very, very fast model evaluations, and then you wrap this model predictive control around a deep learning architecture. I do want to point out that in some cases, you actually need a pretty good model. So this is what happens when you do this on a bad model. Actually, it's not even that bad of a model. It's a pretty good model. And this is what happens when you do it on a good model. So you have to really get good models in some cases. In others, it's not so important. And so what's happening nowadays, there's two major fields where machine learning is entering control. One is deep model predictive control, so using deep learning to learn the model that you then use for model predictive control. And the other one is in reinforcement learning. So how many of you have worked with reinforcement learning? So this is the engine for AlphaGo and for the computers that can beat people at chess and things like that, where essentially if you have a complex, let's see if this starts. So I'm just going to play this in the background. This is learning how to play an Atari game. You've probably seen this before. Chess is a pretty tough game to learn a control strategy to win because there are so many combinatorially many board configurations. You as a human, you have rules of thumb to tell if you're winning or not. Like if my son takes my queen, he's probably winning. Right? It's like the simplest thing is just like count the points on the board. That's one number to assess if a board is good or not. What deep reinforcement learning does is it essentially uses deep neural networks to learn a value landscape of what is good or bad on your board or in your video game. So it learns the same kinds of intuitive proxies for what is a good board strategic position versus a bad strategic position, which would normally be combinatorially expensive to enumerate. Okay? In this case, I really like this example because eventually this deep reinforcement learning learns the advanced human trick. Have you seen this before? Yeah? So it learns the advanced human trick of trying to weaken one side, and then it solves it all instantaneously for it. So this is kind of amazing. The computer actually learned, this is kind of an epiphany, it learned the strategy that an advanced human would have learned over a long period of time. You can also use this for robot playing catch. This one's kind of cool. I'm going to end really soon. But with a few trials, this is a model where they've actually incorporated some rudimentary physics into the learning procedure. So if you do reinforcement learning with no model, and you just try to learn the value landscape, it's extremely inefficient. So download Google reinforcement learning pendulum stabilization and run it on your computer. It'll run for 8 hours before it learns how to stabilize the pendulum, unless you give it some basic physics. And then it can learn after maybe 30, 40 trials. I forget exactly how many it is, but that's about how many a kid actually takes to learn this task. So it's pretty impressive towards human level performance if you bake in some physics knowledge. And then this is one I always show Boeing executives, which is this great compilation video of all of the failures of reinforcement and basic robotic control. So we still have a long way to go. These bodies don't understand themselves. They don't understand their own physics. Oof. Okay, so I'm going to end there. What we're going to talk about on the next tutorial is mostly how we learn coordinates and how we learn models from data using increasingly sophisticated regression and optimization techniques with data. Okay, thank you.